Chapter 7, Waves. Waves. A wave is a periodic disturbance having extension in space that moves away from a source and carries energy, momentum, and information as it goes. Two important categories of waves are mechanical waves and electromagnetic waves. Mechanical waves travel only through matter and involve the motion of the particles of matter they pass through. Sound waves are an example. Electromagnetic waves, which consists of varying electric and magnetic fields, can travel through a vacuum and through matter. They do not involve the motion of the particles of the material they pass through. Light, radio waves, and X-rays are examples. Transverse waves. Transverse waves are mechanical waves or electromagnetic waves in which the particles of the matter through which they pass move perpendicular to the wave direction. Transverse waves can travel only through solids. Longitudinal waves now. Longitudinal waves are mechanical waves in which the particles of the material or matter through which they pass move parallel to the wave direction in a series of compressions and rarefactions. Longitudinal waves can travel through fluids as well as through solids. Examples then of both transverse waves and longitudinal waves. Transverse waves at the top, where you have a crest and a trough, and compression, rarefaction represented at the bottom. The amplitude is the maximum displacement from a normal position of the particles of the medium through which a wave is passed. The wavelength is the distance from crest to crest or from trough to trough of a wave. Examples here. Lambda then is the wavelength of this wave. It is from crest to crest, represents the wavelength. And A is the amplitude. From the 0 point of the wave to its maximum displacement is the amplitude. The frequency is the number of crests that pass a given point each second. The unit of frequency, cycles per second, or hertz. The speed is the rate at which each crest moves. Wave speed is equal to the wavelength times the frequency. So V equals F times lambda. Very simple expression. An example. If 10 waves, each 2 meters long, pass by every second, what is the wave speed? The formula V equals F lambda, 10 per second times 2 meters, 20 meters per second is the speed of the wave. The period is the time needed for a wave to pass a given point. So the period capital T is the inverse of the frequency. Example. Given a wavelength of 50 meters and a speed of 8.5 meters per second, what is the frequency and the period of this wave? F is equal to V over lambda from manipulating the equation, and we get a value of 0.17 hertz or 0.17 cycles per second. The period is the reciprocal of the frequency, and we come out with 5.9 seconds. Standing waves occur when reflected waves interact with forward-moving waves in such a way that some points in the media have amplitude twice that of the normal amplitude, and at other points the amplitude is 0. Such waves appear to be stationary. Now the Doppler effect is another important feature of waves. The Doppler effect is the apparent change in frequency of a wave due to the relative motion of the listener and the source of the sound, named after its discoverer, Jonathan Christopher Doppler. As the relative motion reduces the distance between the source and the observer, the frequency or pitch of the sound becomes higher. As the relative motion increases the distance between the source and observer, the pitch becomes lower. An example.
If you listen to the sound the horn on a train makes as it passes, you'll notice that the frequency is higher as it approaches and lower as it moves away. We'll now demonstrate this Doppler effect using two small speakers mounted on a swing arm. Here is the sound the speakers emit when stationary. Listen to the changes in frequency as the speakers are spun around, alternately approaching and receding from the microphone. This animation shows the sound waves emit.
Resonance is another feature that waves have, and particles do not have this feature either. Resonance is the ability of an object to be set in vibration by a source whose frequency is equal to one of its natural frequencies of vibration. Now, electromagnetic waves, on the other hand, prior to this moment, we've considered mechanical waves, now electromagnetic waves. The big name in this area is James C. Maxwell, proposed that magnetic field is associated with changing electric fields. And as such, electromagnetic waves consist of linked electric and magnetic fields traveling at the speed of light. And here's an illustration here. Radio waves is an example of an electromagnetic wave. For electromagnetic waves, the electric and magnetic fields in an EM wave are perpendicular to each other and to the direction of the wave. As represented here, the blues represent electromagnetic field vectors pointing up, and the red represent magnetic field lines pointing horizontally. The wave is pictured traveling from left to right, and you see the undulations here, and the two fields travel along with the wave. It, in fact, is the two fields that makes the wave. EM spectrum. Electromagnetic spectrum is the range of frequency of EM waves. And here we show the spectrum now ranging from long wavelength radio waves through microwaves, infrared waves, and through the visible range, ultraviolet, X-rays on to gamma rays. And this is the visible range, ranging from about 700 nanometers in length over down to 400 nanometers. The violet are always at a shorter wavelength than the red. And the spectrum is always in this order: red, orange, yellow, green, blue, and violet. You will never have the spectrum in any other order. Light waves. Light appears to travel in a straight path in a uniform media. And although light actually consists of waves, it is useful to represent light's straight line motion as lines called rays. And reflection is a property that waves have. Particles do not have this property. So reflection is the change in direction of a wave when it strikes an obstacle. Refraction is another property of waves that particles do not have. And refraction is the change in direction of a train of waves when they enter a medium in which their speed change. Refraction occurs when waves cross a boundary at a slanting angle. If waves approach a boundary at right angles, no refraction occurs. An illustration: the wave is traveling from left to right, strikes the boundary here, it is refracted, is bent. And when it exits this medium, it also is bent a second time. Color. White light is a mixture of light waves of different frequencies. Each frequency of light produces the visual sensation of a particular color. Example, white light enters this prism and we get then the X in the rainbow colors from red through violet. Notice that we still have this consistent pattern: red, orange, yellow, green, blue, violet. Dispersion is the separation of a beam of white light into its various colors or frequencies. Rainbows are caused by the dispersion of sunlight by water droplets. Interference is another property that waves have that particles do not have. Interference refers to the adding together of two or more waves of the same kind that pass by the same point at the same time. Both constructed and deconstructed interference exists. Diffraction is the last property that waves have that particles do not have. Diffraction is the ability of a wave to bend around the edge of an obstacle. Diffraction waves spread out as though they originated at the corner of the obstacle and are weaker than the direct wave. Illustration. Waves then, that this is the source, it is indicated that the wave is propagating up to the left, but at the corner here, waves are diffracted into the shadow region. So waves always have this property, and you will have some spreading out of waves in region where they normally would not go, but because of diffraction, they spread out into other regions. Because diffraction exists, the image of microscopes and telescopes are blurred at high magnification. The larger the diameter of lens or mirror used in an optical instrument, the less significant the diffraction and the sharper the image. So the resolving power of a telescope is D equals to 1.12 lambda times L over D. So D sub 0 then is the closest distance between the centers of the two objects that you're trying to resolve. Lambda is the wavelength of the light source, and capital D is the diameter of the image forming lens, and L is the different distance from that lens to the screen. So what we see here, shorter wavelengths, you can resolve the distance between two objects with shorter wavelengths far better than you can with longer wavelengths. And if the diameter of the lens forming the image is also large, okay? An example, if then you have two very small lenses, if you have a very small lens trying to form an image of two closely spaced objects, they will be blurred into this airy pattern, as we call it. And if the small but lens, but as the lens gets larger here, you're just barely able to resolve the two discs here. Here, with a very large lens, you're able to resolve the two images. That takes me to the end of this presentation.